Right, so in the last video, I talked about acids and bases. So to start off in this video, I'm going to have you look at these examples from your other paper. Right, I gave you a paper full of examples that were going with the notes. And all you have to do on these six, that are the first six questions, are determine whether each thing is an acid or a base. So I told you what to look for, so you could already do that, but I'm going to go through these real quick. If you want to pause and try and do it yourself and then, check and see if you got the right answers, that'd be a great idea. Otherwise, this first compound, there is a hydrogen in front. This is definitely an acid, right? Whereas this one would be a base because it's got hydroxide in it. I can see that. This one also is a base, right? And I'm just going to assume that this is a base because it doesn't even have a hydrogen in it, let alone a hydrogen out front, right? Ammonium, these three hydrogens are behind the nitrogen instead of out in front, which is the reason that's written that way to begin with. It breaks binary compound rules otherwise. But if I write it this way, with three hydrogens in front and then a nitrogen, it looks like it's an acid. So that's why we write it the other way. This is actually a base. Otherwise, this is an acid because the hydrogen's in front. Water is an acid, but water is also a tricky one, right? If you see water on the quiz we do, water is technically an acid and a base, right? It's a special kind of compound that actually can be both, right? So there's actually a lot of examples of amphoteric compounds like water that can be both acids and bases, but you're not going to have to memorize many of those. Otherwise, with acids and bases, again, we talk about hydronium and hydroxide, right? So water itself acts as an acid or a base, as you can see on this slide. We just talked about that, right? Because it can create hydroxide and hydronium or hydrogen, however you want to think about it, in solution, right? So those are interchangeable. Remember that new hydronium ion is the same thing as a hydrogen ion. Otherwise, since water can act as an acid or a base, it does it on its own in a pure sample. But if you had pure water, the amount of hydrogen ion and hydroxide ion would be very small, right? Notice these two concentrations down below, right? They're 1 × 10⁻⁷ molar concentrations of hydrogen and hydroxide, and they're equal to each other, right? So really small amounts of hydrogen ion and hydroxide ion can be found in pure water. But since it's the same amount of each, that's why it's going to be neutral. That's why it's still going to be balanced, right? So we need to know these numbers because you can use those two numbers. You can multiply those two numbers, which I seem to be missing on the slide here, so I need to add that. So you guys have in your notes that Kw, maybe that's on the next slide over here, but yeah, way over here. That Kw, that ion product constant for water, if I multiply the concentration of hydrogen ion and hydroxide ion, 1 × 1 is just 1. And then when I multiply those 10⁻⁷, I just add the -7 and the other -7 to get this 10⁻⁴. This constant is something I'm going to use a lot in my calculations, right? It's really important that those two things multiplied give you this constant here, right? I'm going to use that for problems like these ones here, because if that's always true, then I can use it from one concentration to the other to find what's missing. If I take that 1 × 10⁻⁴ and I divide it by 1.8 × 10⁻⁶, I should be able to come up with my hydroxide ion concentration. Since they always multiply to equal that constant, I can divide and figure out what's going on. So I'm going to do that on my calculator real quick. -14th divided by 1.8 raised to negative times 10⁻⁶ power. And I'm going to get an answer of apparently 5.5555 repeating, but I only need 2 sig figs, so I'm going to say it's 5.6 times 10 to the negative ninth, right? So that's what I'm going to do over and over again. It doesn't matter which one I have. Remember, hydronium is the same as hydrogen. Hydroxide and hydrogen are always related. So on this next one, if I'm given hydroxide, I do the same thing. I take 1 times 10 to the negative 14th, and I divide by 1.0 times 10 to the negative ninth. Now, if this is the case, it's a lot easier. I don't need a calculator, because 1 divided by 1 is still 1, right? I'll use 2 sig figs in this case. But my exponents, all I have to do is subtract when I divide. And if I take a negative 14 and I subtract a negative 9 from it, I technically just add 9 to negative 14, which makes me have a negative 5 exponent, right? Notice that 9 plus 5 is 14. On the last example, 6 plus 9 is 15-ish, but it would be 14 if these were exactly 1. That's always going to be true. So if you see a 1, right, you don't need the calculator. If you see something besides a 1, like the 1.8, I needed a calculator to come up with my hydroxide ion concentration. So again, here, there's no 1. I'm going to have to do it on the calculator. I'll take my 1 raised to the negative 14th times 10 to the negative 14th, and divide it by 1, what was it? 4.43. Screwing everything up. Let me try that again. Divided by 4.43 times 10 to the negative ninth. And I'll get an answer that says, and I need 3 sig figs, 2.257336, whatever. But I just need 2.26 times 10 to the negative sixth. Always check to see that adding those exponents is close to 14. It's 15 again, but that's because I don't have exactly 1. But always check that, because it can tell you if you did something majorly wrong on your calculator. Otherwise, 4, I don't need a calculator again. It's still going to be 1. But again, exponents add up to 14. 11 plus 3 gives me 14, so it's going to be a negative 11. So that's my concentration of my hydrogen ion. So pretty simple. That's what you do when it's all said and done. The other context that's important is I need to understand that with my ionization, right, how I know if something's acidic, basic, or neutral is which ion predominates, right? Which one do I have more of? Because if there's more hydrogen ion, it's always acidic. So if I look back at this last slide, I know that there's actually more hydrogen ion here than hydroxide ion. Now, you have to think about it, that negative 6 is actually smaller than a negative 9, but in terms of an exponent, right, 6 is bigger than negative 9. So when I'm talking exponents and I got these negatives, right, it's the lower of the two numbers. 6 is smaller than 9, but a negative 9 is smaller than a negative 6. So I have more hydrogen ion, which is what makes this an acidic solution, right? Otherwise, same thing's true here. This is a bigger amount, so this would be acidic. Whereas in this example, it looks like the hydroxide ion concentration is bigger because a negative 6 is bigger than a negative 9, same numbers we had before. So this is a basic solution. And then in the last one, negative 3 is bigger. So this is also a basic solution. Otherwise, when it's all said and done, the only way it can be neutral is if you have exactly the same amount of each. And that's pretty rare, right? So in real solutions, that's not likely to happen. The main situation in which that may happen is if you literally had pure water, like we talked about before. Because then you'd have exactly 1 times 10 to negative 7th molar concentrations of each hydrogen and hydroxide. They'd be the same. Otherwise, in order to get a neutral solution in the lab, a lot of times you need buffers to do it.